Hello everyone, we are Group A and today we're going to present to you guys our project, the Farming Assistance Solar Tracker, or FAST for short. The main goal and motivation of the FAST project is to help farmers. Weather accounts for an extremely large portion of a farmer's crop loss, up to 85%. If farmers had more information as well as better tools, they would be able to better recognize current weather patterns as well as better predict future ones. This would allow farmers to make better, more informed decisions for their fields that would result in greater profits as well as an increased food yield. Providing farmers the tools they need to understand how their field is doing as well as have access to historical data about how their field has been performing previously is the main motivation of this project.
For the team, we have me, Nicole Andrade, Christopher Badalato, Jan Iglesias Morales, and Savannah Irvin. Here we have the member responsibilities. Chris is primarily responsible for the sensor system and application. Jan is primarily responsible for communication and secondary responsible for power and sensor system. I'm primarily responsible for the housing and secondary for the application. Savannah is primarily responsible for power and secondary for the housing.
Ultimate objective of this project is to help farmers farm better. The FAST will send real-time data through an app connected to portable devices obtaining data. This specific climate data will allow farmers to maximize efficiency and reduce crop loss. The specification and requirements needed to reach this objective are broken up by subsystem. The mechanical system needs to house all of the physical components in a housing that is durable and portable. This housing must be able to support solar tracking, so a gear system that allows for stable dual-axis movement is also necessary. Solar panels are the sole power source of the FAST. As the FAST cannot be confined to the grid or it would not be portable, the batteries must be able to power the FAST for at least 24 hours. There are only around 6 hours of usable daylight for the solar panels to effectively charge, so this needs to be factored in when calculating what that battery capacity actually is. The power system must also supply a stable 5-volt VCC line and a 9-volt VCC line, as there are sensors that need to be powered by 5 volts and other sensors that need to be powered by 9 volts.
Other project specifications and requirements are described here. FAST will require communication between child units and the main device. The main device will be required to send data via Bluetooth to the Android application. Each child unit contains a sensor system that provides accurate lux, temperature, pressure, humidity, soil temperature, and soil moisture readings that will be sent to the main device. The main unit will provide accurate wind speed data, accurate lux data from 4 lux sensors for the solar tracking mechanism, as well as the sensor system described previously. Each of these units require an MCU with I2C, SPI, at least 5 digital pins and 3 analog pins, as well as low power consumption. Here, we see the overall block diagram for the FAST devices. The main unit contains 2 MCUs, one to control 4 lux sensors and the solar tracking system, which charges batteries that supply 5-volt and 9-volt outputs for all sensors and MCUs, and another MCU to control the receive LoRa, main unit sensor system, and data output via Bluetooth UART. Red blocks represent MCUs, green blocks represent sensors, orange blocks represent mechanical control of the solar tracking device and servo system, purple blocks represent communication devices, yellow blocks represent power, and blue blocks represent other miscellaneous parts.
The FAST network is how all the individual parts of this project communicate with each other. It's essentially a star network as shown on the right, and the way it works is that all the child units send measurements to the master unit. This allows child units to be added very easily to an existing network. It is extremely long range with tuned antennas, and the main transmission is just an array of measurements that are sent from the child units up to the main unit. The main unit then compiles all of the data and presents it to an Android app via Bluetooth for the user. So when a child unit sends a transmission to a master unit, all they're really sending is a string of bytes, because that's just how LoRa works. However, our child units are taking a bunch of measurements, which are floats, and storing them in a float array. This means that we have to convert the floats to bytes before transmission. This was done using a union data type, which simply maps one data type to another. So we made a union that mapped a float to a 4-byte array. This allowed all of our data to be converted from floats to bytes before a transmission, and then when that transmission is received, from an array of bytes to a float. And then once the data has been processed, the data can be provided to the application for further analysis or just for the user to observe. The payload in each transmission is pretty much just an encoded array of floats. We have an example of one of these arrays to our left. Each index in the array corresponds to a different characteristic of interest. So the first index contains the machine ID, which tells us which child unit sent us this transmission, followed by the temperature, humidity, pressure, and so on. So each float just represents a different measurement, really. The end of each payload is delimited by a -1 so that we know that we have reached the end of the payload. The wireless technology we're going to use to implement the F.A.S.T network is known as LoRa. LoRa is a sub-1 GHz wireless technology that operates in around the 900 MHz frequency. It's relatively low powered, especially when compared to the range it can output. It can output up to 20 kilometers using directional tuned antennas and tuned settings, or up to around 2 kilometers via line of sight. We're using the RFM95W module, which is pictured on the left, for this project. A LoRa range test was performed using a breadboard prototype of a child unit and a breadboard prototype of a master unit. Under non-ideal conditions with non-calibrated antennas nor settings, a range of around 1,000 feet was observed with these breadboard prototypes. At this range, no data is lost and consistent measurements are observed by the masters. On the two pictures on screen, you can see how we performed the test. On the left image, I am holding the child unit prototype, and that arrow is pointing to Chris holding the master unit prototype. On the right image, you can see the distance between the 2 points we were at on the beach, which is around 1,000 feet.
Shown here is the sensor system. Each child unit as well as the master unit contain the entire sensor system, with the exception of the main unit containing the anemometer. Sensors such as the VEML7700, BME280, and the STEMMA soil sensor are read via serial I2C lines, while the others, like the GUVA-S12SD UV sensor and anemometer, are read via analog output. This output is converted to understandable data within the software written to the MCU. Data from these sensor systems is sent via the LoRa transmission described previously to the main device. The BME280 is an I2C device that provides the unit with accurate ambient pressure, humidity, and ambient temperature measurements of the surrounding area. This sensor requires a 5-volt input for power. VEML7700 is an I2C device that provides each unit with an accurate lux reading. For our solar tracking mechanism on the main unit, we require 4 of these lux sensors, shown here, for proper rotation of the tracking device. Because each of these lux sensors has the same I2C address, we require a TCA 9548A I2C multiplexer to receive accurate lux data from each sensor. All sensors and the multiplexer require a 5-volt input. The STEMMA soil sensor is an I2C sensor which can be placed in surrounding soil. It will provide each unit with accurate soil moisture and soil temperature readings. The sensor requires a 5-volt power input to function. The GUVA-S12SD UV sensor will provide each unit with accurate UV index readings. This sensor uses analog output. To get a precise reading, we provide the sensor with a 5-volt input. It will then output a value between 0 and 1 volts. This output voltage is converted to a sensor reading that accurately represents a UV index value. The anemometer wind speed sensor will provide the main device with accurate wind speed in meters per second. Similar to the UV sensor, the anemometer uses analog output, though the anemometer must be provided with a 9-volt input value for comparison. With some testing using multiple fans and a functioning anemometer, we were able to get a linear regression equation, shown here in the graph, to accurately obtain wind speed data. The output voltage from this sensor is plugged in as the X variable, with Y being the accurate wind speed reading.
The solar tracking system is a subsystem of F.A.S.T. The main purpose is to point panels towards the sun for maximum light intensity throughout the day. This will be accomplished by using data gathered from 4 lux sensors in a dual-axis servo system combined with dual gears to provide freedom to follow the light intensity. To the right, we have a block diagram showing how the servos are related to the lux sensors, MCU, and the panel. The sensors are constantly feeding data to the MCU. Calculations will be made based on the sensor values, and these calculations will determine which way the servos must turn. The microcontroller will send signals to the servos. One servo is responsible for rotating the panel vertically and the other horizontally. This will cover both the X and Y axis for a higher energy output. For the mechanical design, we decided that in order to accelerate the development time, we will use a pre-designed 3D model. The model was found on a website called Thingiverse, which provides primarily free, open-source hardware designs. The design chosen is capable of a dual-axis rotation. However, it will have to be modified in order to fit the panels. For the material, we decided to choose PETG for its great durability, and it is also water-resistant. Solar tracking components. We will be using 4 lux sensors and 2 servos. The first picture shown on the right is used for testing. For the final design, the sensors will need shielding to give more isolation for directionality. As for the servos, they will have to be strong enough to power the gimbals and the solar panel weight. We have decided to use 180-degree servos. 180-degree movement for both the horizontal and vertical servos will be sufficient in following the sun's movement. Here we have a rough flowchart of our tracking algorithm. First, we will initialize the servos and put them at a standing position. Then we get values from all 4 of the lux sensors. We calculate the averages for the top, bottom, left, and right sensors. After that, we calculate the difference of the top and bottom, and then left and right. Then we check to see if the average of the top sensors is greater than the average of the bottom sensors. If it is, then we rotate the vertical servos up. If not, then we check to see if the average bottom is greater. If it is, then we rotate the vertical servos down. The same logic is used for the horizontal servos.
Because the size of the solar cells exceeded what was originally anticipated, we had to redesign and reprint the piece of housing where the panels sit. The current design of the power system requires the following components: 4 5-watt polycrystalline solar cells, 2 TP4056 charging modules with input, output, and battery terminals, 2 18650 batteries with an individual capacity of 3000 milliamp hours, a 3.7 volt to 5 volt boost converter, and a 5 volt boost converter. The way the power system works, as well as design choices, are as followed. 2 solar cells in parallel act as the input power source for a TP4056 charging module. 2 charging module inputs were chosen because there are safety concerns with using one charging module to charge 2 batteries in parallel. This is because it is possible the batteries will charge and discharge into each other, acting as a short circuit. As depicted, each of the 2 18650 batteries have their own charging module. The output of both charging modules are placed in parallel together and run to a 3.7 volt to 5 volt boost converter, designed with TI's Wetbench tool. The 5 volt VCC line is then used to boost from 5 volts to 9 volt to create the 9 volt VCC line. A 3.7 volt to 9 volt boost converter was not chosen because of the increased board area associated with that boost when I used the TI Webbench tool.
For communication between the main device and the Android application, we will be using Bluetooth. The HC06 module allows the main device to send data with UART to our Android application. All data received by the main device via LoRa will be sent to the application. For proper functioning, the module requires a 5-volt input. The Android application provides the user with data from each of the F.A.S.T units once it's obtained by the main device. This data is read byte by byte and delimited within the application for easy viewing and testing. In the image shown of the current version of the application, child device 1 and the main device, device 0, are currently sending live data to be displayed. The application will not only show live updated data, but historical record data as well. Listed here are some of the constraints we've encountered so far during the design process. First, working within our original budget has been a bit of an issue as some of the parts have been a bit more expensive than we originally planned. Next, effectively making progress on the design while maintaining a safe environment due to COVID has been a little bit difficult. And finally, learning to develop our project with new equipment such as the soldering iron, hot air rework station, and 3D printer has been a bit difficult to learn, plan, and develop together remotely.
On screen, you can see the PCB for one of the F.A.S.T master units. Each F.A.S.T master unit is going to have 2 MCUs. Each one of these MCUs is going to be responsible for different things in the master unit. The left MCU is responsible for facilitating communication between all child units and the master unit via LoRa. It's also in charge of making all the measurements via sensors for the master unit. The master unit's going to have a collection of sensors, some of them on the board and some of them through breakout boards. The reason for this is that some sensors need to be located far away from the board, such as the lux and the UV sensor, in order for them to function properly. The left MCU is also going to be responsible for communication between the unit itself and the Android app. This is going to be done through a Bluetooth module. The right MCU is solely responsible for solar tracking. It offers pinouts to connect 4 lux sensors as well as 2 servos. The right MCU is only doing calculations in order to ensure that the servo is positioning the PV in such an angle that solar capture is maximized. On screen, you can see the PCB for one of the F.A.S.T child units. Now, the PCB for the child units is very similar to the master unit, however, it has a massive reduction in its total size. It only implements one of the MCUs, and this is the MCU that is responsible for LoRa communication as well as all the sensors, and it implements all of the sensors as well as any headers necessary to implement sensors that cannot be implemented on the board, such as the previously mentioned UV and lux sensor.
Overall successes. Our group has been consistently meeting twice a week, which is proving to be very effective in making great progress. Despite the pandemic, everyone has been working hard on the tasks we are given and have remained positive in attitude. Logic breadboard prototypes were successfully implemented and verified. Costs were distributed. And finally, communication between everyone was constant and effective. Overall difficulties. Designing a power system along with a charging module that can charge both batteries safely has been challenging. The main logic system will be finalized before the power system. This will require the logic and power PCBs to be split in order to accelerate the development time. Finally, financing has also been difficult as the cost of sensors as well as the associated research and development continue to pile up.
The project is currently being financed solely from the members. To ensure costs are evenly distributed, members are responsible to report all costs they incur. After these costs are reported, we will reimburse everyone to ensure that everything is distributed evenly. The budget displayed consists of the summed price of components to create 1 parent F.A.S.T unit and 3 F.A.S.T child units. This budget, however, does not include the costs associated with researching and developing F.A.S.T prototypes. This budget will be used to calculate the costs of 1 F.A.S.T parent unit after more accurate numbers associated with PCB printing are available.
On screen, you can see a chart that details the overall progress of the FAST project. In terms of research, we have made fantastic efforts into learning as much as possible in order to properly implement our project. In terms of design, prototyping, and software development, we have made fantastic progress, and we are more than halfway done in each of these categories. We are now focusing on parts and acquisition as well as PCB production. Overall, we pin our overall progress at around 55%, which is totally in line with our expectations. In terms of progress details, right now the logic system is almost entirely completed. All the major design decisions have been completed, implemented, and validated by the team. In fact, several logic breadboard prototypes have been implemented for the master and the child unit. Currently, the power system fulfills capacity, is able to keep up with the logic breadboard prototypes. However, several redesigns still need to be done. The PCB for the logic board is completed and currently under the review, both for the child and the master unit. And right now, we have a test application that can decipher the Bluetooth data and parse it accurately. On screen, you can see two pictures. Each of these pictures are of our logic breadboard prototypes. Specifically, the top picture is our logic breadboard prototype for a child unit, and the bottom picture is the logic breadboard prototype for our master unit. The next steps for our project is to finish the power system design as well as finalizing the power PCB. At the same time, we expect to send out our first logic PCB revision to be printed, at which point, once we received our PCBs, we hope to assemble first revision units and test said units, at which point we will make any design changes that we need to and then send out a second revision to be printed out if needed.